Just briefly, let me say that I'm here at TMI's research coordinator, very part-time, just 1 day a week. I work full-time at the Division of Perceptual Studies at UVA, co-director of the Westfall Neuroimaging Lab there. I came down to TMI on a part-time basis as research coordinator. I'm probably crazy to do this, but I did it because I see a tremendous potential here at TMI for research. After laboring away mightily in a lab at the university, scrounging for subjects and whatnot, I started coming to TMI on Wednesday evenings at MC², bringing my box of sensors and doing a collaborative study on psychokinesis with DOPS and TMI. I noticed, it was hard not to notice, that virtually every session that we did, there was always at least one and maybe 2 or 3 people who were really making those sensors pop. And it started sinking in that TMI is a really amazing environment, great potential for research because of these residential programs, all the people coming through here who are focused on consciousness expansion, and it really got my interest up, and so I'm hoping to help ramp up research here. I think we started in pretty well this past year. We had 2 programs. So you've heard a bit about this morning, the Journeys to Happiness program in June, in which we discovered that, yes, it's possible to run mass EEG simultaneously on, and that one was 14 people, and not have the program explode in our faces. So we got even more, I would say, ambitious. In December, ran a Journeys, Discovery You Are More Than Your Physical Body program, in which we had 16 people doing EEGs simultaneously, and added some consciousness expansion validation experiments to it. So we were doing combined RVs, exercises oriented towards people acquiring information about remote targets, whether they were doing it as an RV or an OBE exercise, and I'm going to talk a little bit about that. I'm going to talk about the MC² project, which has turned into a pilot study that will be submitted for publication pretty soon. And but first, I'm going to talk a little bit about a lab study. This is some fairly hard core science. One of the first things that Bob and Scooter both mentioned to me when I came on board was, we need more evidence to show that there's a physiological basis for these audio stimuli. Now, there is some published research regarding binaural beats. I would say maybe 3 good studies, 2 of them with EEG, one with MEG magnetoencephalogram, but nothing done on SAM. So we set out to do some basic research on SAM at the most fundamental level, looking for that frequency following response, brainwave driving. It's also known in the EEG world as an evoked potential. Now, evoked potential research is a big tool in EEG, and you can get evoked potentials from all kinds of stimuli: auditory, visual, somatosensory. In this case, for audio stimuli, it's called an audio steady-state evoked potential. The only way that I know of to get those things and actually see them, visualize them, is to run bursts of tones, either binaural beat or SAM, for just 2 seconds. Do multiple repeats of this. In the case of an audio stimuli, you need about 300 repeats. They have to be carefully marked on the EEG record so you can line them all up and average them. The reason for this is that evoked potentials are extremely small. They're running about 1 microvolt level. Normally EEG is in the order of 50 microvolts. So we have a signal that's buried underneath all the other brain activity that's going on. So we designed an experiment that included stimuli from both binaural beats and SAM. These are really basic single frequency, either a single beat frequency for binaural beats or a single SAM warbling frequency. Because you have to do 300 repeats, I could only get 4 stimuli into one experiment. So to give you a little idea of what this is like, we hook up a person. We're running a 19-channel EEG that I loaned the Institute for this. Had to come up with some circuitry to monitor the audio line to tell you precisely when the tone occurs so we can mark the EEG record. Our participant in the experiment is sitting over in the shielded room. We have them sitting up reading a book so they don't start falling asleep, because this is a really exciting experience. It goes on for about an hour. They're sitting here and they hear beep, 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 stuff like that. And I'll just cut to the chase and show you what we found. Here is a driving response for 3 Hertz binaural beats. This is averaged over 15 participants, and I should back up and tell you, to get one of these studies done, you need at least 18 participants in the experiment. For each condition, they're going to have 300, approximately 300 trials run. So in this case, I've got 15 participants averaged up. I ran 18. On subject number 18, the amplifier blew up. So we're in the process of getting that fixed. We have 2 of them that have to be rerun. So these are 15. It's, not the total that's needed, but it's pretty close to what's necessary to see what's going on. What this chart is showing you is the 2-second stimuli averaged, 4,500 trials, averaged out most of the noise, and we're seeing the frequency following response. This stuff right here is the response of the brain to when that tone goes on. Boom, oh, there's a sound. It's called the early components. Actually, in the EEG world, there's names for these things. This is like N100 and P200 stands for negative 100 milliseconds, positive 200 milliseconds, etc. Here, this little oscillation, sine wave-like oscillation, is the actual frequency following response for binaural beat at 3 Hertz. That's a 3 Hertz sine wave. And then here's where the tone goes off. Boom, oh, tone went off. So this is pretty much replicating the studies that we saw in the literature. Gives us a confidence that we're doing this the right way. To give you an idea, though, I mean, this looks pretty easy, looks pretty clean, but to give you an idea what goes on to get a response like this, that's what a single trial looks like at the same scale that what you just saw. The scale we were looking at a minute ago was 2 microvolts. Okay, so at a 2 microvolt scale, a single trial looks like that. That's how big the EEG is. Turn the scale down to 50 microvolts, now you're seeing regular EEG. Another big challenge with this type of research is that somebody sitting up reading a book is going to be producing all kinds of other artifacts. In this case, this stuff right here that looks a little bit bigger, that's Emg Muscle Artifact. And I should just back up and describe a little bit for you. These are the different channels across the head. This is oriented towards, this is the frontal region of the head, moving towards temporal, central, parietal, occipital. These big waves right here are coming about from, that's not EEG actually, that's a muscle artifact. person that was sitting here reading their book was feeling a little bit tense. It's not an uncommon pattern that I see often. It's especially prevalent in frontal channels, forehead, and some of these temporals. So frontal around temporal. Not uncommon to see that. And just to put in a little bit of a plug for Mind Mirror, if you'll notice, back here in the parietal and occipital areas, things are much quieter, back of the head. Mind Mirror folks are taking their electrodes and using differential pairs on the occipital and parietal parts of the head. By doing that, first of all, they're getting away from the very common muscle tension. And secondly, by running them as differential pairs, they're canceling out anything that's somewhat distant from the electrodes, like the muscle artifact, and focusing in on the underlying activity right in that area of the brain. So I thought that was a very clever way of doing their electrode arrangement. That's a very clean EEG. Our subject for that particular experiment is a very good subject. I see him in the room, in fact, right now. Most of the time people are, and this shows up in some of this EEG as well, they're blinking, their eyes are moving, they may be swallowing, moving around and whatnot. You get all kinds of artifact in here. So it takes forever to analyze these things. You have to go through several stages of pulling out the noise, doing a thing called independent component analysis and whatnot. So these kinds of studies are a fairly big investment in time and energy to get done. We started this study, I guess I started building the equipment for it over a year ago. It took all of last spring to set it up. Susan was our test pilot. We had to do several runs, fiddling around with all kinds of stuff to get this thing working. Finally got it underway, and then we had to recruit subjects. We used a combination of folks from within the TMI community and without. We had people coming in from the surrounding community. So we had a combination of experienced users of these audio programs here versus what I would call maybe hemi-sync virgins. People had never heard this stuff before. I can't say that I saw a huge difference between those two populations, but I haven't systematically studied that yet. Our main goal for this particular study was really just to see, can we find physiological evidence for what Sam is doing? That was really the goal of this experiment. Back to the 3 Hertz binaural beats. As you can see, you're getting a sine wave. How can we tell exactly what that frequency of that sine wave is? Just by looking at this particular type of graph. So we go into the frequency domain to do that. Now this is somewhat similar to the stuff that Judith was showing you. These bars are representing the amplitude or power of a particular frequency. The Mind Mirror is showing you sort of wider frequency bands. This is very narrow. Each one of these bars represents about 0.5 hertz of bandwidth. As you can see, the biggest bar for what we were just looking at a minute ago is at 2.93 hertz. It would be nice if it was at 3 hertz, but the sampling frequency of the amplifier is kind of determining where these bars end up, and that amp I was using makes it so it's a little bit off. But 2.93 hertz with a 0.5 hertz bandwidth is including 3 hertz. So this is verifying that 3 hertz is the driving frequency, but you could also see the bar next to it has got a little bit of power into it as well. And that's something interesting that I saw in this experiment, was that not everybody was showing a driving response right at 3 hertz. Some people were a little bit shifted down. I have no idea why that is, but I would say maybe 3 different people had a downward shift in their frequency response. It's not much, but it's just enough to be interesting. Another interesting aspect of this this bar out here, these two are at around 6 Hertz. So it's a harmonic of 3 Hertz. Apparently, you know, your driving response is not limited to just the frequency of the binaural beat. There can be harmonics popping up as well. All right, so I don't think I mentioned this, but our 4 conditions were 3 Hertz binaural beats, 29 Hertz binaural beats, 3 Hertz SAM, and 29 Hertz SAM. Here's the response to 29 Hertz binaural beats. It's pretty robust. That's 29 Hertz right there. As in fact, you can see from the frequency response. There's the 29 Hertz bar popping up. There's some low frequency stuff going on. This bar down here at the very bottom, it's about 1 Hertz. That's caused by this. It's a little bit of that early component still leaking in. I didn't mention, but in order to get the frequency response, I just take the chunk of data that's in between those early and late components, and we're just looking at the oscillatory part of the response. So that 1 Hertz bar shows up in everything. It's just a part of the early response. This is kind of interesting right here. It's 3 Hertz. Why is 3 Hertz still showing up when we're just running a 29 Hertz stimulus? I don't know. Maybe it's sort of an artifact of this experiment because we're running these stimuli, you know, so fast that somebody gets stimulated at 3 Hertz and it's like ringing a bell. That bell just sort of kind of keeps ringing. It's an issue that maybe one should take into account when they're running experiments like this. Maybe you just want to run one stimulus at a time. Nonetheless, as I said, our goal was to discover if SAM has got a physiological response or not. So here's 3 Hertz, 1500 second time average. What that means is I'm taking that chunk in between the early and late components. You see a little bit of the early components still left there. Does that look like 3 Hertz to you? No, I'm not so sure. Here's the frequency response. At 3 Hertz, 2.93, there's nothing there. At 6 Hertz, out here, something shows up. So, you know, maybe the harmonic is stimulated.
I can wait until the end, but we have done a lot of EEGs, based EEGs in the Shili Wellness Center. Not very few brains are specifically following frequency, following response.
Yeah, well, let me just address that, because what I see on an individual basis is a real wide range of responses. Okay, so what this is an average response over 15 different subjects. It doesn't mean that nobody responds at 3 Hertz to SAM, because I saw a couple people that did. Okay, but there is a wide range of variation, individual variation. Yeah. Let me just go on to the 29 Hertz SAM. Now, 29 Hertz SAM, boom, got a response. On average, cross population. These little squiggles, that's 29 Hertz. There it is right there. That's I'm using the same scale here as we did with the binaural beats, so it looks kind of small, but it's there. There's also that little 3 Hertz thing is still popping up. I guess the bell's still ringing from 3 Hertz. 29 Hertz SAM. Okay, here's 29 Hertz binaural beat. It's, I think people are surprised by that, 29 Hertz binaural beat. The lore is that binaural beats is not supposed to really work above 20-some Hertz. But this puts the lie to that. It's there. I put these 2 slides in here so you could compare them. Here's SAM, here's binaural beats. So binaural beats is actually a little bit bigger than Sam. But Sam is there. So I think, we found evidence for driving response in Sam. It's clearly there. What this study seems to be telling us is that, and I think people have actually come to this conclusion already based on experience, Sam works better at higher frequencies. The real question now would be, is there like some frequency range where Sam really peaks? It would be fun to do another study and run higher frequencies and see what Sam is doing there. Because at some point, binaural beats is going to start petering out, and maybe Sam is really kicking in. So, but the good news is we got some evidence here, direct evidence of the driving effect for both Sam and binaural beats. And the next step in this study is actually in the data analysis to go to a thing called current source localization. This can be done even with just 19 channels of EEG. You can get it. It's kind of a picture of where in the brain things are being activated. We can actually get a time course of that. That was done in one of the published studies in binaural beats. And we're going to try to replicate that next. It takes an awful lot of data analysis, so it's going to take a little while to pull that one off. But it'd be really interesting to see exactly where the brain's getting activated and how it travels around, at least in those first 2 seconds. It's kind of like, when the physicists say, oh, we got a model of the Big Bang in the first nanosecond. Here we got a model of what's happening in the brain in the first 2 seconds upon hearing one of these binaural beats or SAM stimuli. So that's the next step. That's the goal. When we get that done, we'll be probably posting that on the blog site, and our intent is to get this published in a mainstream journal, like Clinical Neurophysiology, something like that. Yes, Jim?
How does this compare with what Skip did?
Well, Skip was doing bands.
No, he had an evoked potential study.
I've seen that study, and it ended up being sort of a statistical study looking at the increase in like a band.
Because I know he and I talked about it, and the methods and such, the average evoked potential approach was exactly what he was doing. And
well, then I haven't seen that specific one. I know the one that was done that didn't get published. It was more of a statistical band study. Yeah, we have to make this quick because I've got a lot of stuff to do. But
I understand that 3 megahertz or 3 hertz would be an oscillating tone. That 100 over here and 103, I get a 3 hertz.
yes,
But wouldn't 29 hertz binaural? Wouldn't you hear the separate tones and not hear the warble? Wouldn't you hear an oscillating tone instead of a warble?
And Ross, excuse me, could you repeat the question since there's no mic on the question?
oh, okay, sure. So the question is, at 3 hertz, you'll hear that binaural warble.
Yeah,
At 29 hertz,
you'll hear an oscillating tone.
yeah, geez, I
Does
don't
that
know.
work to also?
Well, all I can tell you is what's popping up here in the EEG. And I have seen one study about binaural beats where they were running even higher frequency than this and getting that response, which is still, as they claim, it's an illusion. This is not coming from the actual signals itself, it's manufactured in the brain.
And the oscillating tone manufacturers. Wow. That's significant.
Okay, well, now we're going to take a walk on the wild side. So in June, we ran the Discovery Journeys program, as I mentioned, and in December, we added the RV and the OVE targeting as a means of maybe getting some data, research-oriented data, to show that people were actually doing some consciousness expansion type experiences. What we did was ask them in their exercises in the morning when they were down here hooked up to EEG to either tell us what's in the picture inside this envelope. It's an RV-oriented exercise. Or tell us what the object is in that little box up there behind the beam. Some of you maybe can see the bottom of it. So little objects. And this was an OBE-oriented type task with the idea that, oh, hey, you know, it's right here. You can just float out of body and kind of go up there like Pam Reynolds. I don't know if any of you know about the Pam Reynolds story. Pam Reynolds was a lady who was undergoing surgery and floated up out of her body over the scene in the operating theater and happened to look up at a little shelf by a window and saw a tennis shoe up there. You could not see that from down below. After the surgery was over, she says to the hospital personnel, you know, you got a tennis shoe up there on your shelf. By then, there's no way there's a tennis shoe up in there. You ought to go check. They checked. Sure enough, there was a tennis shoe up there. So, you know, this seems like a fairly easy thing. You don't have to go through any walls. You can just float up here and look in there and see what's there. I'm not sure anybody actually did that in the December program. But we had some really incredible results in the RV and OBE tasks. Some, especially with these objects up here on the shelf, there were some folks that were drawing perfect pictures of them. This little Santa Claus dude right here, one of our participants drew a really right-on picture of it. We had a vase, a multicolored little vase, that one of the participants drew it to perfection. She showed the side, she showed it from the top angle, she listed the colors, and not one piece of superfluous information. It was perfection. So anyway, the beauty of this kind of setup is that you can keep data on it and you can get scores. We had an independent panel of judges comprised of TMI staff, volunteers, trained by the master himself, Joe McMonigal, scoring all of our participants' target reports. And what kind of results did they get? We put this all together in a spreadsheet, blah, 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 ranked them based on the judges' scoring. Judges blind, of course, to the targets and whatnot. And we had, let me see here, we had 110 valid trials. Of those 110 valid trials, 38 first place scores, you know, from this group. The probability value for that is 0.007. That was pretty amazing. So I think something like this demonstrates a potential for research here at TMI. I was really gratified to see that not only you know, we can generate data like this, you can correlate it with what their EEG scores or EEG activities doing, and the participants in the program are getting great benefit from this. I mean, it was really exciting for them. I mean, it's not only a validation of what they're doing, but you know, they're getting all the feedback from human operators on what their EEG is all about. So this was a lot of fun. I found it really exciting and rewarding experience to participate in a program like this. There's a third aspect that we can do in a program like this as well, and that's some sort of instrumentation to try to measure, say, is there a field that's being set up by this organized activity and consciousness expansion, possibility maybe putting sensors up there with the target, so if somebody's visiting a target, is there something that's getting shifted a little bit? We've got an experiment like that in the works at DOPS. So I tried just a preliminary approach to this in the December program. I put a random number generator back in the utility room and let it run for the duration of the program. I'll quickly tell you about RNGs. Random number generators generating a string of bits, zeros or ones, that are random. Okay, there's precedent for studies like this. They have been actually here at TMI. There was a study done, published by Dean Radin and Skip Atwater in 2007 in the Journal for Scientific Exploration. They used multiple RNGs scattered around, had 3 of them actually over in the building next door, running while gateway programs were in effect. They did 14 gateway programs. They also had some RNGs located a little distant from here. And then they also ran this whole setup for 8 controls when there were no programs happening at TMI. And what they were doing was comparing sequences of bit streams for the 3 local RNGs from program to program under the hypothesis that if the RNGs were being affected by some sort of group field effect, you would see a correlation. Whereas if they were just strictly random, there would be no correlation whatsoever. And they did find a correlation, some great p-value as well. And it's a cool study. So I decided to see if I could at least get a start in on something like that. I had one RNG available to me. As I said, I stuck it in the utility room in the back. It's a little bit different. We're not looking at the whole week-long as an experimental run. I tried to distill this down into individual exercises for each day, with the idea that maybe we could get some scores on the exercises, maybe see if they correlate to the target hits that people were getting, whatnot. And the results are interesting. Here's the first day, Monday. Let me just tell you a little bit about what this graph means. In this particular case, I'm looking at what's called the deviation from the mean, accumulated deviation. It's not a sociological term. This is how many bits are starting to add up in excess in either direction. If it's too many zeros, you're going to see this particular line going down. If it's too many ones, the line's going up. So this blue line is sort of corresponding to how many bits in excess you're getting in either direction. The red line is 2 standard deviations out. Anything that's going outside of that red line is considered to be interesting. If it's inside the red line, that can be just considered to be random behavior. So on our Monday morning exercise, and at this point I've only evaluated these for the entire morning session. So each morning session included two different exercises, one oriented towards RV and one oriented towards OBE. At this stage of the game, I've just got them lumped together. But you can see this thing's popping out of 2 standard deviations, and that was corresponding to the first exercise of the day. Maybe Bob might be interested in some of this because, what particular audio program was that causing that? And so it goes back down and it starts trying to climb out. This was clearly during the second exercise. So I saw that when the first one I came up, first one I analyzed, I go, oh boy, yeah, this is really great. And have to do controls. So for the controls, I chose the equivalent time occurring in the afternoon from lunch up till about 4 p.m. When things were starting up again. So it's a time off, people aren't here in the room, there's not this sort of coordinated mental activity. Hey, where are we? Okay. Tuesday afternoon. So maybe people are still a little bit coordinated with each other during lunch because it's popping up against a 2 standard deviation line, but more or less it's not doing anything else for the afternoon. And I also did, just for fun, looked at the overnight. So they're kind of drifting down. I don't know if that's meaningful or not, more zeros than ones overnight. But it's not going outside of that 2 standard deviation line. All right, Tuesday morning. Popping up against it, but nothing major happening. Tuesday afternoon, even less. So, in sort of a contrast, it still appears that there's a little more action going on when people are here focusing on things than when they're off on break. Wednesday morning, something really happened right here, kaboom, and it does pop out the 2 standard deviation line for a minute. Otherwise, it's just kind of cruising along. Wednesday afternoon, this is the story. You get a little action there at lunch again. As people must really like lunch here. I know. But then, this big behavior down here at the bottom. Well, it turns out that Wednesday afternoon there was an optional exercise that folks were doing. Now, it wasn't here in this room, it was back in their check units, but it was happening right here, right in that time frame. So that's not a very good control to use. So what I did was I flipped over to Wednesday morning, and I think probably the mornings before everything gets going here might be a better time to do the controls. I didn't have Monday morning control, that's why I was using the afternoons. But as you can see, Wednesday morning, boy, there's really nothing going on. Okay? Thursday morning. Big action again. Now what's interesting about this is, Monday morning we got action, Thursday morning we got action on the RNG. Monday was the beginning of the experimental run, Thursday is the end of the experimental run. This is something that's been seen in parapsychology research. It's called terminal salience. People get an increase in scoring at the beginning and at the end of their runs. Maybe it's because in the beginning everything's kind of new and interesting. At the end they're just glad it's all coming to an end, but I don't know. At any rate, that seems suggestive. And then Thursday afternoon, nothing. So, what is the takeaway on all this? I did do a little bit of comparison. I ran a correlation for the number of number 1 scores on RV versus the maximum Z values for each session. I found a weak correlation there of 0.7. I also did a t-test looking at maximum Z values for all the experimental sessions versus the controls, and that was approaching significance. It wasn't quite significant, but it was approaching it. I think it suggests, this is just one program's data. Something like this probably needs, several programs worth of data to pile up to get the experimental, thank you, results. So I think it's worth doing. It's suggestive, and I'll keep at it, maybe figure out some other sensors to do with the targets. One last one in the remaining time I have I want to tell you about is MC² studies. So since about 2011, I've been coming over to TMI in a collaborative study with Division of Perceptual Studies, looking at PK. I was trying to develop sensors for use in our PK studies with psychophysiology at DOPS. We didn't really want to use random number generators. We were looking for something, more along the lines of what John is doing with the biophotons, some direct measure that will respond reasonably quickly so we could correlate these with EEG. So I was building all kinds of little electronic sensors, sticking them in a box and bringing them down to Wednesday evenings at MC² and letting the groups have at it. And that's been very interesting, and over time I've managed to develop a sort of stable hardware platform and a stable protocol, and we've got enough data now that we've put together a pilot study I'm writing that up, and that's going to get published probably, hopefully soon, as soon as I can get it written. But just quickly, the sensor that everybody was really affecting is made with these quartz cubes with electrodes on the side of them and a really high impedance electrometer amplifier. Frank DeMarco knows all about this thing. He's whacked at it several times at DOPS. I never knew what these things were doing, to tell you the honest truth. Stuck them all in a box, double shielded, 130 dB of electrical shielding. You know, no electromagnetic field's really going to get in there and mess with these things. Or if it is, it's going to have to be from some really huge source. What they produce are these pulse-like events. So in a way, it's another random event generator. But with maybe some extra added interest to it. If you filter them, you can, get these events isolated and start counting them. It's a Poisson distributed, blah, blah, blah. At any rate, we can get statistics on these things. And there's also an extra added twist, as I mentioned. It will pick up some continuous signals. It really shouldn't. But this little sine wave-like thing occurred. I witnessed this personally. There was a massage therapist from Romania, MC², was sitting in front of the box doing this. And when that happened, when it did, now I know with 130 dB of shielding, the only way that happens from a classic electric field sense is that she had like 400 or 500 volts on her hands. So you could say, oh, maybe that was just a static charge. It was a really wet night, damp. Nobody was doing static charge. Not only that, but if it was static charge, you'd see it on all the channels. It's only showing up on this one channel. It's odd stuff. And we have other evidence like that of odd electric field effects on the sensors at DOPS. Some people are able to generate some really oddball stuff. I've seen it with Joe Gallenberger, for example, when he's doing his business lighting up the fluorescent lights. We ran a little test. I had a static field meter. We went down in the basement somewhere up at RMR on another one of those damp nights that nobody's doing static charge. And I put that charge meter, he's got a few hundred volts accumulating on his body. So there's something really interesting going on with that. Quick plug for the copper wall room. I don't know if anybody's been mentioning that. We're going to put a copper wall room up in our RMR this year. So those of you who know about copper wall rooms, if you want to find out more about it, Google Elmer Green Manager Institute copper wall room, and you'll see what we're talking about. They're measuring electric fields on people. Some people, like healers, meditators, seem to be able to produce anomalously high electric fields. And I've seen this on one particular person that comes to our lab, again with that little handheld static meter. He can be sitting there quietly in a chair, and you just see the charge building up on him. I'll have somebody sitting next to him who's not a healer per se, hold the meter next to them, no charge building up on them. So this is I think could be a very interesting line of research for TMI. We got to quit. Am I done? I'm done. I'm done. One more thing. Let me just say one more thing on that pilot study we ran in MC². We got a p-value 0.03 two-tailed on MC² groups trying to affect those sensors. So difference between their attempts versus controls. So I thought that was pretty cool. Anyway, all right, thank you.
Thanks, Ross. Thank you very much.